Okay, we're going to go into IP addressing, the connectionless is the word I was looking for, connectionless portion of the TCP/IP. The reliability in the TCP/IP, we always talk about those things together, comes from TCP. We could also use UDP with IP office. But the topic areas for this one is configure IPv4 addresses, IPv4 subnets, and hopefully you don't cringe when I say the word subnet. I don't know what method you've been through or taught or learned or whatever else. I'm going to try to use the one that Todd Lamley uses in his book, which I think is a little bit quicker way to get things done. We're not going to have to write out all the binary. We'll do some where we will write the binary. And then do them not really the shortcut method, it's called the increment method. When we do a magic number. Magic number is a little more intriguing, I guess, than and then IPv6 addresses, managing the network addressing, and then a little bit of troubleshooting of TCP/6 addresses. There are a number of labs that are in this section. We'll try to get to, or should get to, the start of the IPv6 before we end today. So topic A in this one, configuring IPv4 addresses. As you know, probably know, should know, I'm sure you know, we're out of IPv4 addresses. Out of means that ICANN doesn't have any more addresses. IANA, actually, the numbers people, doesn't have any more addresses to assign. It doesn't mean that every address that's available is being used, because in the front end of the internet, startup, the basic, there were a number of universities and businesses that were in the developmental end. They got some really big subnets, or Class A's, for instance, and Class B's. Are they all gone? Yeah, they're all issued. Are they all in use? But anyhow, it's a 32-bit binary number represented in a DDN, dotted decimal notation, 4 8-bit octets, and the 8-bit octets get us from 0 to 255, which gives us 256 different digits in this thing. Remember, in networking, that 0 represents something. It's not the null set. When we're doing network addresses, the 0 typically are all zeros in the host portion. And the class full addresses, terms that you probably have heard and we'll do again. The class full portion, the 0 represents the network. It's connectionless. Every network interface needs a unique address to communicate with the network. And these here are the private addresses, and we can look at things, and we may have some situations where we have the same address within our own network. The uniqueness is on the internet, that each device has to be uniquely identified. Otherwise, you might find the same device in two different locations. Not the same device, but the same address in two different locations, different devices. But we need uniqueness in these things. And that's why we're running out of, or have run out of, IPv4 addresses, because everything has to have one. And the Internet of Things, the explosion of devices on the Internet, kind of, I think, caught a lot of people by surprise. There's like over 4 billion, maybe 4.25 billion IPv4 addresses. And that's just a phenomenal number to me. When we look at IPv6, there's 340 undecillion, and I didn't even know what an undecillion was. I learned the word, and I'll show you that number written out when we do IPv6. It is some of the descriptors of IPv6 is enough. IPv6 addresses, enough addresses for every person who's ever lived on planet Earth to have 5,000 addresses. Are we going to run out? Not in my lifetime. You can see by that. Probably not in your lifetime. Probably not even in your children's lifetimes. But it could, because when we started this business, or not we, they, the smart guys started this business, when it got started, they didn't think we were going to run out of IPv4 addresses, but the utilization of the internet, it's one of those things that businesses probably really can't conduct business without it anymore. It's something we have become very dependent, and the addressing is a big deal. The binary to decimal conversion, one of the things, probably one of those been there, done that, to do them. pretty straightforward. Let me go to my scroll pad here in CF to start the pen. The pen, I updated the pen and it worked well for a while, and now it's gotten back to when it's running, a lot of other stuff won't work on my... We have placeholders, just like in base 10 we have placeholders. Base 10 we have 1, 10, 100, 1,000 on down the line. In binary we have 1, 2, 4, 8, 16, 32, 64, 128. I think that gives us a 1, 2, 3, 4, 5, 6, 7, 8 bits. If we add all of these up, it's going to be 255. And we know it's going to be an odd number because there's a 1 down here at the end. The binary to decimal conversion, pretty straightforward process. So we have a 1, 0, 1, 0, 0, 0, 1. First place I know because of this is going to be an odd number. So it's going to be 128 wherever the 1 is, plus 0 plus 32 plus 16 plus 0 plus 0 plus 0 plus 1. And that would be what? 3, 8 2's 10, 3 2 5, 160, 176, 177, I think. So no real issue going that way, I think, when we do these things. Going the other direction, going from decimal to binary, probably not an issue either, but let's see. Let's do this. Let's convert this one back and see if we get the same set here. So what we would do is write the 1, 2, 4, 8, 16, 32, 64, 128, write our decimal number here, and then go and look at our little table. Is 177 greater than or equal to 128? And the answer to that obviously is yes. And we'll put a 1 under the 128 and subtract it, 9 and 8, 17, 49, and subtract it from the 177. Is 64 greater than or equal to 49? The answer is no. 32? Yes, it is. And then we'll subtract the 32. 17. Is 16 greater than or equal to 17? Or is 17 greater than or equal to 16? And the answer to that is yes. We'll subtract that. We get the 1. And brings us over to the 1. So subtraction method, the way I was taught originally was a division that you don't even talk about. You divided by 2 and then took the remainder and go on. I don't remember how to do it anymore. The subtraction method, once I learned it, it's like, okay, this is the way to go. A very straightforward way to go from decimal to binary, just simply by writing the chart 1, 2, 4, 8, 16, 32, 64, 128. Big deal, big advantage about binary. The good thing about it, all you got to do is be able to multiply by 2, because each of them is a multiplication of 2. And as an aside, just as a security thing, that each time in the security world, each time you add a bit to any kind of an encryption process, you just doubled it. You double the strength, because every bit that we add in a binary number, which you're talking about this method before, Justin? Yeah. I think it's a pretty easy, it's pretty straightforward, isn't it? Bing, bang, just subtract it. 1, 2, 4, 8, 16, 32, 64, 128. Another number, if we want to do one, let's do one other one. Let me get rid of this. I don't know. I'm a collector. I've collected a lot of things over the years, and this is one of the things that I finally collected. Too late to do me a whole lot of good sometimes, but hopefully it'll do you some good. So let's do a new one here. Get rid of the eraser. Let's do 206. 206, greater than or equal to 128. Yep. And we'll subtract 128 from it. 8, 16, 9, take with 2, 7. I think that's right. And 8, 8, 16, 6 and carry 1, 7. 2 is, 7, 2 is 9, 1 is 10. 1 and 1 is 2. 78 greater than or equal to 64. Yes, it is. 64, we're going to get a 4 and a 1, a 14. 14 greater than or equal to 32. No. Then 16, no. Then 8, yes. 6, greater than or equal to 4, yes. And we'll just say 4 and 2 is 6. We can see that. And then a 0 down here. So the decimal to binary using the subtraction method. Hopefully straightforward way to do that. Going from binary to decimal, not a big deal. We need the table here, the 1, 2, 4, 8, 16, 32, 64, 128, and even in a testing environment, probably useful to have this. And one of the things, and I don't know how many people have taken tests, that's going to happen to you when you do these testing, or at least in Cisco, unless they've changed that too, and I don't think they have. When you go in and sit down at the test, you're going to have a few minutes before you actually go in to start answering the questions for score. You're going to have scrawl paper, although I understand the ones at home you can't have a scrawl paper. You can write some things down, just kind of put them in your head before you walk in. You get this sheet with the erasable marker, write these things down. Write the 1, 2, 4, 8, 16, 32, 60. Any other little thing that you might need in order to do that. You will have a few minutes. What they do is go through this is the way to answer a question. This is a multiple choice question. This is a drag and drop question. The different methods that they have. And they, again, unless they've changed it in the Cisco world, and I have no reason to believe that they do, on the multiple choices, they tell you how many, or the multiple answers, they tell you how many. And if you make a mistake, if you don't have enough answered and you say next, it'll say you too few selections. And if you have marked too many selections. So they don't try to trap you into those kind of worlds or let you make those mistakes. Binary conversion, each group of 8 bits is an IP address that can be converted. And we're going to do the same thing here in an automated fashion. Can be converted from its decimal form to its binary form, or vice versa, using the 1, 2, 4, 8, 16. 172, same thing that we just did. Was 172 greater than or equal to 128? The answer is yes. Put a 1 in the 128 position, subtract the 128. Is 44 greater than or equal to 64? And we're going to say no. So we'll put a 0 there. When we get to the 32, absolutely. So we'll put a 1 there, subtract it. Is 12 greater than or equal to 16? No. 8, yes, and then 4 greater than or equal to, and then the zeros at the end. And the rest of them are just filled in here. To get the binary addresses of the 172.16.40.155, what it would look like in binary. Computers don't use words very well, don't use words at all. They use numbers. Way back when development was going on, they actually tried to use base 10 and use the voltages. The problem happens, though, that if you set up a scale for base 10, and we have markers here, and I'll probably miss the markers here, but 1 volt, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, 8 volts, 9 volts, 10 volts. Yeah, we got some spares up here. But based on the voltage level, you have the base 10 number. Problem that they got into was, what happens when you have voltage, an irregular voltage? So sometimes that didn't work. The ones in the zeros representing the decimal numbers that we're accustomed to work best, because when we looked at that video the other day on what it's represented, a positive voltage represented a 1 and a negative voltage represented a 0. Those are probably going to be consistent, so that's why we use binary. Voltage variations, yeah, you could do that, but you could also wind up with a whole bunch of errors because of the unregulated voltages that might happen. The parts of an IP address, and this there again, kind of a been there, done that. We're going to have a network portion, and we're going to have a host portion. And the subnet mask is going to be the thing that tells us how much of the address each of these things. The network address, by definition, and we'll get to these, but I like to get these in and say them a lot of times maybe. This one shows the subnet mask here is zeros. When we AND the devices together, the network portion and the host portion, when we AND these things together, and in an ANDing process, a 1 and a 1, this is not addition, this is ANDing, Boolean algebra. A 1 and a 1 is a 1. A 0 and a 1 is a 0. And what you actually wind up with is when you AND these things, wherever the 1s are, you get those binary numbers again. And wherever the 0s are, you get 0s. The network address, the network portion, the network address, by definition, is where the host bits, the node portion, the host bits are all 0s. When you do the ANDing, what is the network address? What is the broadcast? Broadcast address is where the host portion is all 1s. So network portion, and then when we AND the 0s here, the portion is removed by the subnet mask. Since it gives us all 0s in the host portion, we're going to, it's going to be on that particular network. The IP address types, 4 types of addresses: unicast, let me just go ahead and bring these up: unicast, anycast, broadcast, and multicast. Anycast is kind of an interesting one. See if my browser will work with this, because what it does is allows us to have not unique addresses. Everybody said, hey, you got to have unique addresses. Now I'm going to tell you, we don't have to have unique addresses. This is the root servers. This is the DNS in action here. And what I want to do is go to, I think most of you guys are in Colorado. So we have these in Denver, and I think I could get an F. I'm going to write down the address, and you can too, as soon as I find a pen, of the F server. And when we do DNS, the F server is the way that it is represented. It's going to be 192.5.5.241. 241. So that's in Denver. Let's go to, I think that we have, that they lived in Houston. We have an F server here. It's the same address, 192.5.5.241. What that means is that if you're in Houston, you can go to the Houston DNS server to do the lookup. If you're in Denver, you can go to the Denver one. The anycast goes to whichever one can best service you. We'll say the closest is something that we would say that would be, thanks Justin, that would be, the closest would be the term that would mean something to us, but the one that can get you the answer the quickest is where you're going to go to. So anycast has to be configured as an anycast address. It's kind of interesting. It's not actually technically supported in IPv4. It is in IPv6. But many nodes with the same address, only one receives the data, or in this case, only one receives the request. Broadcast, we've looked at the broadcast a couple of times in order to demonstrate some of the characteristics of the switch. Broadcast goes to every node that's on that particular network. And when we were doing the switch, it went to every node that was connected to the switch, regardless of whether it was on that address or not. And that was where the VLANs come in. Just try to, whatever here. And the next one here is a multicast, an address that identifies a subset of nodes. And what I had up along with that, let me get rid of the other one. This is from Network Sorcery. What do multicast addresses mean? And these are the multicast addresses. 224.0.0.0 is a base address. 224.0.0.1 is all systems on this subnet. All routers on this subnet, 224.0.0.2. Distance Vector Multicast Routing Protocol. OSPF, the one that we'll be doing, 224.0.0.5, all routers. .6 designated routers, 2 different ones. So how do you get to be in that multicast group with OSPF? You'd be a router and have OSPF installed as the routing software to do these things. And we've got ripped down here EIGRP, IGRP, the different whatevers, DHCP server and relay agent 224.0.0.12. to do all of these things. And the list goes on and on and on. Not that you have to memorize them, but what is it? And it really is typically going to be a localized or an ISP. I'm just reading an article because you always get curious about who's using what. It says, does Netflix use multicast? Would kind of make sense, wouldn't it? So that they have all these people that are watching the same movie. You don't have to have individual connections to them. You can send it to the multicast group. And the multicast group would then they would then pick it up from that multicast group. And the way you would get to be a member of the multicast group is because you're watching a particular movie, maybe, to do that. But it's never been implemented on the internet. So it is a local or a networking thing. Windows, and I don't remember which one it started with, but one of the Windows servers started with the install the Windows operating system on the workstations from the NIC, boot to the NIC, and then get the install files downloaded and install it, while you're asleep at night and set it up on a schedule. Had set up a multicast. You were able to set up a multicast group for those that were going to install it. And how do you get to be a member of that multicast group? You booted from the NIC, and then it streamed that data to those particular locations. Everything didn't have to have an individual unicast connection in that case. Makes things a little bit more easy. IPv4 address space is divided into classes, and probably been there A, B, C, D, E, and there is an F also, and that's what I was looking for on that one. The reason that we have classes is that when we first started using, and he said he thinks it's XP, and it could have been XP that started booting to the NIC. The multicast was, and you could do XP with it, depending on which ones you put on the server. But it was one of the server early, not 2000, but one not far after 2000, that set up the ability to do a multicast group. But anyhow, back to this, the classes, when these things first started, there weren't any subnet masks. So classes would then be used to dictate how much of the address was network and how much of the address was host, so that routing would work. So if we're not using subnet masks to tell us how much of the network is, how much of the address is network and how much of the address is host, we have a problem getting to a network. And that's what the classes were all about. It says class A 1 to 126 for unicast. It actually goes 1 to 127. 127 is the loopback address. 127.0.0.1 is the local host. If you ping that, you're pinging the local host on your the local host of your machine. The 0 is used for a binary 0. The 0 is used. It's going to be used for the default route. The 0 actually represents any IP address, any network address to do these things. So class A 1 to 126, and the binary numbers over here can help you out if it's one of those that I don't want to remember all of this stuff, and we can have our 1, 2, 4, 8, 16, 32, 64, 128. We can have those and remember the class A's start with a 0, 1 to go through these things. So if we had all ones here up to this one, if we had a 1 here, if we did all that 1, 0, 0, 0, 0, it's going to be 128. So 127 is going to be all of these others if you add them up. The next one, and I'll try to do a different color for each one of these. The next one, the pink's pretty close, but the next is 0, 1, 1, 0 is going to be the most significant. This is going to be an A B here, so this is going to be 128. The next one is going to be 1, 1, and when we add these up, the C is 192. So the B starts with 128. We can see that, and it's going to end with 1 less than the next network address, so it'll be to 191. The next one, the class ABCD, is going to be a 1, 1, 1. If you add that up, 192, it's going to be 224. So it starts with 224. This one is going to be 1 less than that, which goes to 223 for the class C's on down the line. So that's what these binaries represent when we do those things. A, B, C, D, and E, there's not enough. E is experimental. I got carried away there. D is multicast. Multicast addresses 224. Typically, they're going to be 224.0.0. something when you go back and look at these things. The listing that goes 224.0.0.0 on down the line to 0 to 0 to 255 until we get to way down here 224.0.1. but I don't think that any of these in this list go beyond a 224.0 something another when we do those things. Well, there is down here. Internet Control Block 239, but that wouldn't be anything that we'd be concerned with for those. So 224.0.0 something, 224. Something is going to be what the multicasts are going to start with. Multicasts don't have subnet masks, by the way. When we do this, the Class E, the experimental, I've seen experimental military use on down the line. The bottom line is that we can't use them. They're reserved addresses, and nobody knows what they're reserved for. But they're not in use, won't be in use, because hopefully we're going to get converted to IPv6 as we go through this. The kind of a summary here, the Class A, the network address, and we've talked about a little bit about the subnet mask, how much of it is network and how much of it is host. And you see the progression. Class A, the first octet is network, the rest of it is host. Class B, 2 octets are going to be network and 2 octets are going to be host. Class C, we're going to have 3 octets are going to be network and 1 is going to be host. The summary slide, how many addresses do we have in this thing? And if you look at the Class A, 16,777,214 host addresses, and you see that it's got 2 to the 24th minus 2. The reason we have to subtract 2 from each of these is we have to have 1 address reserved for the network address and 1 address reserved for the broadcast address. We can't assign those. Those can't be used from one to the other. Class B, 65,000 addresses. Class C, 254 usable address. A little more reasonable, but we talked about the VLANs this morning, and what we wanted to do was create broadcast domains. Can you even imagine what the broadcast traffic would look like in a Class A network? And that's where we come in a little bit later with subnetting. We want to break this thing down into smaller chunks, smaller network portions, so that we have a better control of it. The advantage to something like this would be we could consolidate addresses, and I'll talk about what happened or what our friends at Virginia Beach did, and it was a pretty clever way to do things. Actually, we could talk about it here. We used a 10.60.x.x, and we subnetted it with a 24-bit mask to 255.255.255.0 /24. CIDR notation is how many ones in the mask, in the subnet mask. It's the only thing that represents. Shortcut way to write the subnet mask. So within the network at Roanoke, we might have 10.60.10.0, 10.60.20.0, 10.60. And you get the idea. Everything starts with 10.60.30.0. So when the folks we had to use the /24. At Virginia Beach wanted to send something to Roanoke, all they had to do is say, hey, everything that starts with 10.60, send it to Roanoke. Everything that starts with 10.50, send to Greensboro. Everything that starts with 10.10, keep at Virginia Beach, on down the line. So break these things down. And what the subnetting does for us is allows us to have smaller chunks at the destination, but measure it or manage it in bigger chunks at other areas. It simplifies the routing tables a little bit when we do those things. So the default subnet mask, the / CIDR notation, how many bits are in the subnet mask. 0 to 127, the first octet, what is going to be the value in it, and then the high order bit 010, what we just saw, the number of possible networks in these things, and the number of possible hosts. As we increase the masks in the network portion, we get a whole lot more networks possible. We got 2 million in the Class C, but we have 254 usable, 256 addresses, 256 minus 2. Have to take out the network address and have to take out the broadcast address to do these things. So in the Class A's, we got 128 networks that are available there. The one on the right, the private IP address ranges, and we're going to have slides for these things. But the private address ranges are what we use inside of our networks, and we'll do NAT next week, network address translations, where we translate the private IP addresses, because they're not routable on the internet, to a routable public IP address that our ISP gives to us. The 10 network, the entire 10 network, that's a whole bunch of addresses, 16 million addresses that we can use there. Well, the Class B is kind of chintzy. They use a 172.16 to 172.31.255. 172.32 will be the next network address. 192.252. And its subnet mask will be 255.240.0.0. The Class C's, and I was trying to do it on my, was calculating the subnet mask. The Class C is the entire 192.168.255.255 is assigned to us for the private IP addressing. But when we use those addresses, we use a 24-bit / 24 255.255.255.0 subnet mask on those. Again, a pretty good summary chart here. The special ranges, all zeros is used as the default route. We'll do that when we do routing. 127.0.0.0, the loopback address. 169.254.0.0/16 is the automatic private IP addressing, the APIPA address, one that you never want to get, because what it says is my device is configured to get a DHCP, an automatic address, and I can't find a server. So let me give myself an address. And it's going to be masked with a 255.255.0.0 subnet mask, and it will not have a default gateway. It can be used to communicate within that broadcast domain, but it can't go through the router. It's not going to be routed. It's not going to have a default gateway to get out of that particular area. Useful boundaries here. The address 110. The Class A address boundary between the first and second octet for these things. And this is kind of the same thing that we've been talking about here to do these things. 172.16, the Class B boundary between the second and third octet. And then the Class C between the third and the fourth octet. And it is, again, dictated, all these things are dictated by the subnet mask. Subnet mask tells us how much of our network is how much of our address is network, and how much of our address is host. Why is the network so significant? Routers find networks. They don't find individual hosts. Once they get to the network, the ARP protocol that we looked at earlier is going to find the individual host by resolving the IP address to the MAC address and then sending it to the MAC address. Whole process, lots of steps goes on. Lots of smart people did that. The private IP addresses used to build the internal networks, the ones that we use. The enterprise networks we use, and LeaderQuest uses. I think LeaderQuest uses the 10 address space. We use the 10 address space. You use that at home. If you do an IP config in the command prompt of your machine, it's probably going to be a 192.168.1 something or a 192.168.0 something. Those are typically the addresses that the wireless routers will give out for these things. And then again here, the CIDR notation, classless internet domain routing is what that is for. It shows the number of bits out of 32. If it was /32, that would be a host. All ones would be an individual host if you wanted to mask it that way. But the / tells us how many bits are in how many ones are in the subnet mask, how many bits that are ones are in the subnet mask. Can be divided into subnets, not routable, can't be used on the public address. And the firewalls, these are called aliens. Aliens are things that you shouldn't have, shouldn't see or shouldn't go through the firewall. But what you should do on your firewall, just in case, is to restrict these addresses from coming in or going out when you use them. The unicast, I don't know that we necessarily, but we have a nice picture here for it, that an address that is used to identify one node. Packets are sent from one node to another node. When you went this morning to LeaderQuest, or just to get here to the Zoom, you went to an individual IP address, and it was resolved, and we'll look at DNS, resolved from the name to an IP address. The packets from one node sent to another node. All the other nodes are going to ignore the transmission, and now we're getting down to it. We kind of got an idea of why that happens because of the MAC addressing, and the devices only accept information to their address. Other nodes are not identified by the unicast address and ignore the transmission. Unicast addressing is predominantly used in local area networks and on the internet to get to places we want to go, a web page, a mail server, an FTP server to download something, a download server. Those kinds of things are going to be unicast addresses. The Anycast group, and we have looked at, and hopefully by looking at those things, the Anycast is like, golly. And when I first saw this thing, I said, golly, I didn't know you could do that. I knew you could do a round robin in a DNS, but that's where you have the same name represented by multiple IP addresses. But in this case, we have the same IP address, and we're going to go to whichever one is closer to us. The delivered data to one node in the network out of the many with the same address. The other nodes are not part of the Anycast group. The DNS server farm is a good example for that, the Internet root name servers, and that's what we were looking at when we did that. And you've heard over the years probably that if you can take down the 13 name servers, you can take down the Internet. And yes, if you can take down the 13 name servers, you can take down the Internet. And these are the 13 name servers. And there's 288 down here in the southeast U.S., and then we divide them out and go to the East Coast and in the Washington area and go on and on and on and on and on as to how many there are. There have been attempts to bring it down. The reason Washington's got so many, it's one of the entry nodes to the Internet. There have been attempts to do that, and they actually have, the attackers actually have slowed the Internet on occasion to do these things, but the server farms to do that. The broadcast, we've looked at that. We've done broadcast a couple of times just to see on the switching and how things work to get to see where the data flowed through the switch and what we would do and wouldn't do, could do and couldn't do. Identifies all the nodes connected to the network when we do that. Typically used to check the availability of services. And when we get into DHCP, DNS, find different things. DHCP, when you're trying to get a DHCP address, you don't know what the address of the DHCP server is because you don't have an address. So you send it to the broadcast, say, hey, DHCP server, if there's one out there, give me an address. And since I don't know my IP address, I'll just put all zeros in it as my source IP address to do these things. Used as a legacy method to locate other methods, the ARPs, WINS. The WINS is a very old system. I think that it probably is still incorporated in Windows, but not really used. It's Windows Internet Name Service. It's a broadcast protocol that is incorporated into a server. It's just a way of doing that. Used by servers to advertise their presence when we do things. Also used to advertise the presence to network nodes. Used by servers to advertise their presence and used by servers to advertise presence to network nodes. Huge amounts of traffic, and that is the reason that we remain concerned about broadcast traffic and broadcast domains. We want to minimize the amount of traffic as well as kind of give a little bit of isolation, separation, segregation of the functions on the network. The kind of things we've talked about, and I try to use things that you say, oh golly, I don't want those guys talking to each other. Payroll, and then maybe just typing pool or whatever else. Who do you want to be able to see the broadcast? Because if you can see the broadcast, you can say, well, maybe I can get there then. Let me give myself, so I can see the broadcast, then I know I should be able to communicate. Let me get an address there and see if I can go in and give myself a pay raise to do these things. Broadcast storms are an issue. Broadcast storms were what brought down our layer 2 before we did spanning tree. It's what brought down that network in New York New York and Chicago that we were talking about to do those things. The IPv4 address, the broadcast address, is all ones. 255.255.255.255 is the broadcast, and that's the broadcast for everything on the network. Let's see. I want to do. There are two commands that I come off the top of my head to find your routing table on your device, or route print and netstat-r. The route table here, 192.168, and this is the active NIC that goes here. The destination 0.0.0 with a 0.0.0 mask default gateway. That is a default route, what it looks like. And then the interface that it goes out of, 1.27, is the address of the NIC that's on this thing. 127.0.0.0, net mask 255 on link. The interface 127.0.0.1 when we do those things on down the line. And then we have 127, a broadcast here, with a mask of everything on link on down the line until we get down to this one, 192. Now, where did that one come from? Probably because I've got multiple NICs on here. Let's see. Here's the network that I'm on, 1.1.125, and multiple NICs, virtual NICs are on here. 1.255, the mask for everything on link. This is going to be the broadcast, and then we have the broadcast to any device. The 192.168.1.255 will go to everything that's on the .1 network. The all 255s is a universal broadcast. It goes to anything that is within earshot of the device itself. The multicast, we looked at a little bit what the addresses looked like and what would be a multicast address, what kind of services would use a multicast. That's used to identify a subset of nodes on the network. Subset, the OSPF routers would be one. IPv6 is going to have one. IPv6, all devices that have IPv6 installed has, when we get to that, it's going to have a multicast address. IPv6 routers. EIGRP would have one. RIP would have one. Generally, if you look at a list like that at Network Sorcery, it's the services typically the services that are installed on it. Yeah, we still got it here. So the multicast, back to the multicast address, base address. All systems on this subnet, all routers on this subnet. So we have one here is all systems. That includes all the workstations, all the routers. It's just all the routers that are there. OSPF, two different types of those, and you can go down the list of the different things that are available for multicast. How do you get to be a member of the group? In this case, you got to be a router and you got to be on this subnet. In this case, OSPF, you got to be a router and you got to have OSPF protocol, routing protocol installed on you. And once that happens, then you're a member of the group and you can communicate with other members of the group. Other nodes not part of the multicast group are going to ignore the transmission. Video server transmitting TV signals is an example of this. Bandwidth conservation due to reduced traffic and server loads. We're going to have some functionality, some functions that go on with this thing. What makes it work? What makes it efficient when we would do it? So the interface condition here, and this one just kind of shows up. Show IP interface brief, and we've looked at that a couple of times. But this is, I think, worthwhile looking at again. And let me get a white pen in here that'll mark on this thing. When we have this, we have the status here. The status here, this is going to be the layer 1 condition. And the protocol here is going to be layer 2. So if we have an up, down, and up, 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 up is what we want to see. This one's down, down. Administratively down means we've given it a shutdown command. We want to see up, up. If we see up, down, we need to start looking at what's happening, what protocols at layer 2, what's wrong with our layer 2 protocol. If it's a down here, then we need to look at layer 1. And if layer 1's not working, layer 2's not going to work with these things. So the status, what we have for these things, and the automated is going to show us that the physical connection, the layer 1, and then the logical connection, the layer 2 portion would be there. Apply shutdown on the interface. You'll see the situations administratively down, protocol down. Apply command and no shutdown command. If we have no cable connection, it's going to be a down and a down. Up, down status. A good cable connection, the right layer 2 protocol configuration is going to be an up, up. A bad cable connection, bad cable, wrong layer 2 protocol, up, down. For these things, and up, up is the configuration that we're always going to want to see. You must see the 2.3 as a status up, up, up is the status we want to see in the show IP interface brief. You can do show IP interfaces, gives you a whole lot more information, gives you a long string. The brief gives you the little brief summary of what is going on in the system.